Greetings, physicists. Here we're going to do some how to solve wave problems here. Basic wave problems. So we'll have, this is something you've probably done, and I bet when you were a kid your parents taught you how to time thunderstorm, or the flashes of lightning in a thunderstorm. Well, we're going to get into some of the math here so you understand the physics behind it, at least in a deeper way. So you see the flash of lightning, and then after 8 seconds you hear the thunder. Let's see what we got. There's two waves going on here. If we draw this, here's the cloud, and here comes the lightning, and here you are way over here. There's a light wave from the lightning. It emits a light wave that goes like that, which your eye picks up. But it all, and that takes a certain amount of time. So from time zero we could say, time equals 0 is the moment when that bolt of lightning strikes the ground. And then there's like time 1, which is when the wave of light hits your eye. Now, at the same time as the light was created, there was a pressure wave created, right? The lightning bolt striking through the air pushed the molecules around it, and that's the vibration, or that's what's going to cause this vibration of air molecules. But they don't travel as quickly as the light. So we have, at time 0, both the sound and the light are generated. At time 1, the light hits your eye. And at time 2, the sound hits your ear. So you actually are missing something. Because essentially, and this is hard to think about, I guess, this is a tricky thing to think about, but you saw the lightning flash a little bit after it actually happened, because what you saw was the beam of light hitting your eye, and there was this time interval while that light was traveling. So essentially the lightning bolt happened just before you saw that flash of light. And then, the thunder hits your ear. So if you do this, so there's like time 2. Time 2 is the time essentially between time 1 and when the sound wave hits. So you see the flash of light, then you hear the thunder. If you start your timer right when you see the flash of light, you're starting at time 1, but you won't be able to get time 0 from that. Does that make sense? So, and honestly, when you see the flash of light, the sound wave has also traveled a certain, so at like time 1, maybe the sound wave is here. So what you're missing is this little bit of time. We're going to make an assumption. I'm going to show you the speed of sound in air. That's the speed of sound. I'm going to show you the speed of light. And we use c for the speed of light. So, I mean, if you were to compare those, right? 1, 2, 3 sig figs, but the highest one is up here in the hundreds digit, which is back here. 1, 2, 3 sig figs is up here. So, in essence, we're going to ignore the time that it takes the light to travel to you. That's just such a small fraction of time compared to the time that this takes to travel to you, especially because the number they gave us for the time, for the 8 seconds later, right? That's the time from time 1 to time 2, has only 2 sig figs in it. So really, we're the imprecision we get by ignoring the time it takes for the light to travel to you is less than the 2 sig figs that we had already. So it's not going to be a problem. In other words, this time at the beginning is so small. that you're going to be missing less than a millimeter in terms of how far away this lightning strike occurred. So what we're going to do is then say it really doesn't matter the light portion of this. What really matters is the time that it took the sound wave to get to me. I'm going to assume that that is, for all intents and purposes, the actual from time 0. So the velocity of sound equal to the distance the wave traveled divided by the time that it took the wave to travel to me. Well, the time it took the wave to travel to me, we're approximating as 8 seconds, and the velocity we're approximating at 343, so I've got to multiply those two together to get x. So delta x will be equal to velocity times time. That's 343 meters per second times 8.0 seconds. Seconds will cancel, and I'm only keeping 2 sig figs. 343 times 8, and I get 2744, or about 2,700 meters, which is close to 3 kilometers. That's not too bad. This is first semester stuff, right? This is basic. This is the first equation we ever got, and it still applies to light waves. So keep that in mind. We'll still use it. All right, let's keep going. Okay, here's another one, a sinusoidal wave. Sinusoidal wave. So it's a transverse wave with an amplitude. So I'm going to draw the amplitude on here. That's 1.5 centimeters. And a frequency of 100 hertz. It's hard to draw frequency. Travels at 200 meters per second. I should put a number there, not just a unit. In the positive x direction, write the equation for the displacement of the wave as it travels. So we have this is a sine curve. Whoops. This wave is a sine curve, and we have a general function for a sine curve is y equals a sine, and then you have to put all the stuff in the middle, and then for this particular wave, this wave would be 2 pi over lambda times x. So notice that if we draw like a graph here, that after 2 pi here, we would have gone 1 full lambda. So 1 full wavelength would be the same, our x anyway, would be equal to a lambda. Well, I don't mean to say the whole thing is equal to lambda. So in that sense, you would get lambda here, which would, sorry, drawing. You would get lambda here, which would divide through with lambda. You would get sine of 2 pi, which is nothing, right, which is the same as sine of 0, and you would get 0 amplitude for y, and that makes sense, okay? So we can write this general equation for the shape. Now, this is just the shape of the wave as it is right now. Then we have to consider the fact that it's also moving, that it has velocity. So if we wait time t, where are all these points going to be shifted, right? Well, they shift forward a little bit, right, like this. This would be the second piece. So this x position right here is going to be x, but you also have to get rid of the distance the wave travels. Well, if the wave is at a constant velocity, v equals x over t, so multiply by t, you're going to get x is v times t. So I'm going to have to subtract out how far it moves forward. So that's there, and then I'm taking the sine of the whole thing, that business. Okay, so the y position, or the vertical displacement, would be equal to a sine of 2 pi over lambda times the x minus vt. And then we can plug in what we happen to know for this wave. Nope, I wanted to stop. Scrolling is hard. All right. what do we know for this wave? Well, the vertical displacement will be equal to the amplitude. The amplitude is 1.5 centimeters, or 0.015 meters, times the sine, 2 pi over lambda, the wavelength. Give me the wavelength. This is so, oh my gosh, really? Really? They don't give me a lambda, but they do give me a velocity and a frequency, and v equals f lambda. And real quick, if v over f equals lambda, and v is 200, and frequency is 100, then lambda is 2. So they gave us easy numbers there. This is not going to work for me, guys. Okay. So frustrating. All right, lambda is 2. Oh, good, that's going to be nice. All right, times x, which is x minus 200 velocity times time. I think that's good. Now, the other thing we have to... That's an equation with two variables in it. Because the displacement depends both on y and on x. Although, we could also do something like... No, I'm not going to bother with that. All right, I think this is all right, because both of those variables will contribute. So, equation with two variables. Not fun, but I think it answers what they were looking for. All right, lastly, boat moving to the right, 5 meters per second. Okay, here's our boat. 5 meters per second. Ocean wave moving left. We have 2 meters between the tops of the crest and the bottom of the trough. I'm assuming that means that is 2 meters. So that sounds like a vertical measurement. So that's twice the amplitude, right? There's a line here, an imaginary line that you can draw, and an amplitude only goes from the midpoint. So our amplitude is actually 1 meter. Period is 8.3. Lambda is 110. That's this distance here. And we got a couple questions. How much time does it take to travel from the crest of one wave to the next consecutive crest? So for the boat, it's got two motions going on. It has an up and down motion as it goes across the waves, and it has a forward motion. Now it's going forward at 5, but the wave is going backward, and we don't know how fast the wave is going backward. So essentially we're going to have to add those two velocities together to get the total speed of the wave relative to the boat. So to get the velocity for the wave, v equals f lambda, but we don't have frequency, but frequency is just 1 over period, so which is also equal to lambda over period. So the velocity of the wave will be 110 meters divided by 8.3 seconds. And the calculator is going to tell me what that is. 13 and a quarter, it looks like. So this velocity is 13.25 meters per second. I will round that later, but for now I'm just going to say if the wave is going this way at 13 and the boat is going this way at 5, that's a total change per unit time of 18 meters per second. So it's as if the wave were sitting still and the boat was traveling forward at 18 meters per second. All right, let's do this then. So how much how much time does it take to travel from crest to crest? Well, from crest to crest is actually can be just a horizontal distance, or we can solve it using the horizontal distance, and that horizontal distance is the same between any two crests, which is 110 meters. So we have a velocity of 18. I'll round it at the end. Trust me. 18.25 meters per second, equal to a delta x of 110 meters over a delta time, multiply by delta time, divide by 18.25. And I get, 8.3. How about that? The same as the period. That's cool. So the time it takes the boat to go from crest to crest is also the period of the wave. Interesting. Well, what's next? Next bit says how much total displacement does the wave undergo? Oh, this scrolling is really bothering me. I'm sure you can tell from my voice. The thing is, there are two displacements here. There's this horizontal displacement, like that, but there's also a vertical displacement. The boat goes all the way down to the bottom of that trough down here, and then all the way back up to the top of that crest. So it actually goes through that 2 meters twice. So if you're going to calculate the total displacement, I'm just going to do this. It goes 2 meters, or not total displacement, total distance. The total displacement is different. So it goes down 2 meters. It goes back up 2 more meters. And then it travels forward 8.3 seconds at a velocity of 5 meters per second. Now, I'm doing that because that's the boat's speed. And the boat's speed is not really going to be affected by the wave. The wave is just going to pass right through it. Remember, waves don't transport matter, they just transport energy. And that kind of passes underneath the boat. So the boat goes up and down 4 meters, but we're only going to use the boat's velocity times time to see how far it goes. So let's do 8.3 times 5. And so it actually goes 41.5 meters forward plus this 4, so 45.5, which if you round it to 2 sig figs is like 46 total meters that this boat travels during that time. The reason now, I know that seems odd, right? It's only going 41 meters forward, but it went from crest to crest because the crests themselves are 110 apart, but keep in mind the wave itself was traveling during that time, and so the wave passed underneath it, and so it moved the other however many meters relative to the boat. This is how far the boat traveled relative to like the surface of the earth. Tricky stuff. Okay, hopefully this was helpful for you in solving wave problems.